class is recording, let's say. Good. How are you?
Okay.
Surviving?
Yes.
Okay. Good. And you're just at the beginning of it. Good. So it's because of the classes that no.
It's cold.
Ah, because it's cold. Okay.
We don't have heating in the guest house.
There is no eating in the guest. Well, because they have to. Because they haven't turned it on. I think they have turned it on by the end of the week.
No, we have more students coming in who will be quarantined. So
Uh-huh.
as long as they're in quarantine, there can be no heating.
Why?
I
I don't know. The virus like the cold, so I don't know.
It's really cool.
It's really big.
Ah, no, I know why. Because the eating is like circulating. Oh shit. Yes. Sorry, this was recorded. Sorry, guys. Good. Great. Great. No, not great. I'm sorry to hear that. Okay, so let me say a couple of things, and then I'll stop talking. So how these Q&A. I mean. So everything should be self-explanatory from the videos in terms of organization of the course, etc., etc. The only thing I wanted to say right now is how I'm thinking about these Q&A. So what are they for? How should we go about them, etc., etc. So in my opinion, so we have to take this as an opportunity in the sense that in the usual setting, what we do is that I come to class, then I talk for 2 hours. Sometimes you raise your hand. Most of the time, like you look at me like I'm a crazy guy from some planet. And then I go to my room, you go to your room, and then you spend like hours and hours saying what the hell this guy said. And then next time you come with a few questions. So, but then in those 2 hours, basically you have to write, you have to understand what I'm saying, you have to understand what you are not understanding. So the idea is let's try to do something different this year, given that we have these conditions, and try to do it in reverse. So I'll give you the videos, I'll give you the material, I'll make an effort to make it as readable as possible. So in principle, I give you everything you need to have to understand what I'm saying. And then we come here and we discuss. So I never plan anything I never prepare anything for these 2 hours, for this hour and a half, whatever it is. The goal is that you come with questions, comments, etc., etc. What kind of questions? I think that there are typically 2 types of questions. One type of question is, in minutes 3 of the second video, it was a plus or a minus. That I think the best is that you post this kind of questions on Slack. So when you have you need some clarification, which is basically a yes or no, or there is something I don't understand, or something that is really a clarification, post it over there so everybody sees it. If there is a major mistake, I put a plus and there was a minus, and all the 10 videos that follow from them are wrong. I can take them out and put them again, right? So I can correct, or I can correct the notes, etc. So this space is not about clarifications. I mean, today, it's okay also to talk about that, but I think the best is you have questions about, that is not just, that calculation. It's more, I didn't understand why we did that, or I didn't understand this whole part was completely unclear to me, etc. Okay? So try to put as most things as you can on Slack so we can see what's there, and then if it's not clear, we can discuss it. And I think that this space is also good to... Hi, Idris. There is someone there. Sorry. Hi, Idris. Yeah, we will have also the Zoom after, but you are most welcome to come, to stay here. So what I was saying is, so I think it's also good if you don't have questions, but you want to, something more like going deeper about some topic, you are curious about something. It's really a discussion. It's a Q&A, but it's also Q&A and D discussion, right? So it's not just you ask question and. But I tend to speak too much, so I'll stop talking. Okay, so yes, so go ahead. Yeah.
Can I have a suggestion?
Yes.
Because during your lecture, sometimes your pointer is like you point like, look at this.
Oh yes, yes,
Yeah.
yes.
So
Thank
it's
you.
so hard to.
Okay.
Where is the pointer?
Yeah, that's a good point. Yes, I should write and then yes.
And what should you write?
Or maybe a larger.
A larger pointer. Yeah, no, but I should like highlight and then I can go back immediately, so that it doesn't stay on the notes. Yeah, that's a good point. Thanks for the suggestion. Yes. Yes. Go ahead.
Can I ask the first question?
Yes.
We have a relation dv over dt is equal minus dv over dx
Okay.
power 2. And you said that we can always write this.
Yes.
Why?
No, I mean, okay. The always there is, I mean, should be contextualized. So we started from x dot equal to f of x. Okay. And what I was saying is always I can define a function v equal to the integral from some point c, whatever that is, choose it as you want, dz f of z. Okay? So the always actually means every time I can write this, what I said after it follows. Right? So if f of z has a pole in the domain of integration, of course you cannot do that. But, and this is a good point, in this class we'll always consider function f which are analytic. So all the derivatives exist and they are smooth and they have all the nice properties you want a functions to have. Okay? So we will never, of course you can find like specific example where that doesn't apply, but this is like actually what you need here. Okay? You want to say yes? Okay.
And how we drive the relation I told you, dv over dt?
Yes, exactly. So now, given this, you agree with me that dv over dx, sorry, let me put a minus here. So you agree with me that dv over dx, dv of dx is equal to minus f of x. Okay? So that means that x dot is equal to minus
And how
dv dx.
we integrated that?
Yeah, it's the, I mean, you know that the derivative of, I mean,
Yeah,
the
I
derivative
see.
is the inverse operation of the integration, right?
Yeah.
So if you derive, I mean, you can see it multiple ways, but if you derive this, I mean, this one, it's almost a definition of this, right?
I understand.
Yeah, okay. So then we write this, okay? And this is just using these properties to write that. And then we can say, okay, instead of following, let me write actually. Yeah, one thing that you will learn is that I have a very schizophrenic notation. So sometimes I call things in one way, another way. Let's call it this way. Okay. dx dt, okay? Just the same thing, just with a different notation. Right? Suppose that instead of saying, I want to know how x change over time, I want to know how the value of this function change over time. And this is what I did, right? So I say, well, what is dv over dt, right? Well, v is a function of x, right? And x is a function of time, okay? If you want to be more explicit. So I have to take the derivative of this, and this is equal to the derivative of v of x over x, the derivative of c over t, if you want to put explicit dependencies of these functions, okay? But now, what is this? Well, I can use this property here, and so this part here is just minus dv over dx, and therefore it's exactly this term here with a minus in front, and I get dv over dx squared. Okay?
Okay.
That is just the algebra if you want. Okay? So this is like a calculation. What this means, okay? What is the meaning of all of this, why this is interesting, why this is useful. Why this is interesting, why this is useful. In your opinion, it's not an exam, just why do you think I am doing this? Not the class. Why I'm doing this specific calculation?
Probably to change the variable in the system.
Yes, we are changing the variable, but why do I change the variable using this precise function and not something else?
That's because if the function depends both on t and x, it's more complicated to.
Well, that's true, but why I want, let's not talk about what I did during the calculation. Why did I want to write the derivative over time of this function?
We want to visualize the flow of
Okay.
the dynamics through
Yeah.
time.
Mm-hmm.
That's why we changed it.
Well, but we can visualize also the dynamics of x, right?
And
So let's say that I have, let's be specific, let's say that I have logistic growth. If I have logistic growth, so I have dx dt equal to r, let's call it n, so rn 1 minus n over k. Well, I can look at n in time and see that it does something like this, or if I start above, it does something like this, right? Why do I want to write, instead of writing n of t, I'm saying something about v of t over time?
regardless of
Sorry? Sorry, the mask problem. Right? No. Why are we interested in this v in the first? Why I started to write this v as the integral? Why am I here doing this?
Regardless of the initial.
Well, the initial condition, I mean, it matters, right? This is an equation for v. It matters what is x of 0, because that is going to be the initial condition of v, right? So what I mean is that this is going to have some trajectory, right, over time. And this trajectory is going to depend from the initial condition. Right? Why am I going into this trouble of v? What is the cute property of v?
I think because that in a large time it will become independent of the initial condition.
That's true also for x, right? Also, that's correct, but it's true also for x, also, or n. Also, x or n become independent, right? In that first example, it doesn't matter where you started from. You're always going to go to k, right?
And it's always, the system is tend to minimize the...
Exactly, that's the point, right? This function is peculiar. It's I mean, it's interesting, it's useful, because its value is always going to decrease, right? So I could have, for instance, here, I could have chosen another function. I could have defined, let's say, g of n equal to e to the n, right? Or actually, I could have chosen just this log n. I could have written the equation for this. I would have found that g over dt was equal to r minus e to the g over k. If you do the calculation, you get to this. And if you plot g over time, here you have log k, and you would have found something like this, right? More or less similar to this, okay? This is a legitimate function, and I can study what is the behavior of g over time instead of n over time. The interesting properties of v is that v always decreases over time. Okay? Why? Because I've just shown you. Okay? So this is the motivation. This explains why this v is interesting. Right? If I define this quantity here, defined this way, what I discover is that their value over time is minus something that is non-negative. So the derivative over v over time is non-positive, which means that it cannot increase over time during the dynamics. So no matter what is the initial condition of v, it will always decrease during time. And property 1. Property 2, this is equal to 0 when dv over dx is equal to 0, which is when f of x is equal to 0. So if you are in a fixed point, you're going to stay there. If you are away from a fixed point, the value of v is going to decrease, which means that the fixed points are the extreme of this function, and the stable fixed points are the minimum of this function. Right? But this is basically shown by this equation here. And in fact, if you think about what is this function here, well, what you're saying is that the Ex is following the gradient of v. So this is, you can interpret this as a algorithmic way to minimize a function, right? If you wanted to minimize a function, what you can do is to follow the gradient of that function. In this case, it's a one-dimensional function, but what you can do is that you can write a, you can basically follow the gradient, and therefore you minimize v, okay? Now, here we started from this to show that that applies. In general, if you have a function you want to minimize, you can use this as an algorithm. This is what you see, okay?
And in case of logistic growth, how we can interpret the v?
How can you interpret the v?
Yeah.
Well, it's the potential, I mean, okay. What do you mean with interpret?
I have a problem. This is the, for example, logistic growth, and I modeled it by the map.
Yeah.
And I want to know what's the meaning of each variable, each function.
Well, I mean, the point is not that v is, how can I say, it's not something that has a biological interpretation itself. It's not something that you say, oh, I go around and I measure the potential, right? But this is true also in physics. I mean, it's a different concept, but the potential in physics is not that you go around and you measure the potential, right? It's something that you know, the potential depends on other parameters, you measure its effect, you can say, oh, the energy is conserved, and therefore I measure kinetic, I measure speed, therefore I have kinetic energy, and therefore I can measure the potential, right? But it's not something that you, so, and here it's similar, right? You don't go around and measure something on the population and say, oh, this is the potential. To measure the potential, you have to have a model in mind, okay? And the model you have in mind is, for instance, logistic growth. So in the case of logistic growth, you know that the potential is Rn minus Rn squared over 2 plus Rn cubed over 3a. Right? You know that this is the potential. So if you know the population and you know that it follows logistic growth, you know the potential, but it's not something that it's useful. I mean, it's not that you say, oh, the potential is 37.
Is it just a mean for calculating the n? Yeah.
I mean, it's a concept. The point is, it's a conceptual tool, right? So if you, I mean, you can see two ways. So the point is that in one-dimensional systems, there are many ways to solve the equation, and therefore they are all tautological. This is going to be different when we're going to play with things in dimension higher than one. The point is, it has a conceptual value, right? So if I give you whatever dynamical system, and I don't tell you anything, I just tell you that the potential is something that looks like this, okay? You can tell me immediately what is the behavior of the system, right? What is the behavior of the system? If I start here, where do I end up? Here, right? If I start here, well, if I start at the top, I stay there, but that is an unstable fixed point. If I'm here, I'm going to go down here. If I start here, I'm going to go to plus infinity. Right? So given the potential, I tell you everything about the long time behavior of the system. Okay? But what is the value of this doesn't tell me anything. Also because, right? That's the point. If I tell you I'm in this point, don't tell you anything. Also because, as you noted here, I have the freedom of choosing this C, right? And this C changes by an additive constant definition of V of x. What I'm saying is that if I define V of x, or I define V of x plus A, whatever that number A is, it doesn't change anything about the dynamics, because the only thing that enters into the equation is the derivative, right? So this disappears. Right? So I have the freedom to choose what is the... Right?
questions.
Sure.
If someone is
I mean,
online.
sure, you organized, you decided.
Okay. Coming from more basics, we were at first modeling the growth of one bacteria in a time.
Yes.
We told that it's duplicate the amount of the bacteria in 30 minutes.
Yes.
And at the end, the formula we got was 10 power T. And
Oh, I see. So I just, yes. Sorry, I interrupted you.
okay.
Yeah, but I think I got, okay. So why 10 and not E?
Not 2. I mean,
Okay.
I think it
So-
must be 2.
Well, the point is, it depends what quantity you define, right? If you say the duplication time, so the time that it takes for one bacteria to become 2 bacteria, okay, then it's true that if you look at the population over time, this is 2, it's like the population in 0, 2 to the time divided by the duplication time. Okay? If this is the time it takes for one bacteria to become 2 bacteria, right?
Yeah.
But then you can equivalently define another quantity, which you can write this way, okay, where R is log, this is the basis is E log 2 over tau, right? So this tau is the duplication time, but I can also define, I mean, this is just algebra again, this R, which is the growth rate, and it's equal to this quantity.
In a matter calculation, I started to counting. I have
Yeah.
one bacteria, and 30 minutes after I have 2 bacteria.
Yes.
1 hour after I have 4, and yeah, it was going like this. But at the end, suddenly it become 10 power T.
No, I mean it depends on what it depends on what you define to be 30 minutes. Do you define to be 30 minutes this tau here, so the duplication time, or you define to be 30 minutes tau over log 2? Okay. I think I said growth rate, and what I meant is that this quantity here was 1 over 30 minutes. And the 10 is just a trick to look at orders of magnitude, right? So in a similar way, I can write this as n0 10 to R over log 10, right?
Yeah.
T, okay? And this is just, correct, right? And this is just a trick to have an idea of the order of magnitude, because you know what is log 10, right? And then you divide and you get it.
But at the end, we must have the same answer, yeah?
Yes, the answer is the same, because all these quantities are defined. I mean, all these equations are equivalent, right? I just changed, I mean, when you change the basis of the exponential, you can just rescale these and you get the same answer.
Well, I think the answer might be different if we start counting by our
No, it depends what you define to be 30 minutes. If you define tau to be 30 minutes, it's one thing. If you define this to be 30 minutes, it's another thing.
And I have a problem with that tau. What does really tau mean? It has no dimension, yeah?
What? Tau, it has dimension. It's a time.
1 over...
Tau is a time, and 1 over tau, so R is 1 over tau.
But we defined the tau as R multiplied by T, yeah? And R itself was 1 over T.
Well, that was a different story. I think that was a different, that tau was coming in a different part of the lecture. That was when we were looking at logistic growth and we were rescaling time, right? That is a different, it's just let's rescale time, so we measure quantity to the same unit of time. But that was a different tau, right?
Okay, so
yes. Yeah, I mean, it's, yes, this is a good point. I mean, I was saying about being schizophrenic, but it's really impossible to have that the variable tau here has the same meaning of the variable tau that I'm going to use 2 months from now in one evolution class, right? So there are finite letters, and we use many of them, and 4 times you use t tau and s at most, right? So always like try to understand what the notation means in that context, right? Don't extrapolate.
And another thing
Mhm.
is car. Why when population grows and they use all the resources, they still remain in the car? The number of them becomes near to car.
Ah, that's a good point. Yes, yes, that's a very good point. The point is that, okay, so if you have a finite amount of resources and those resources are never replenished, of course, at the end there is going to be nobody, no resources, no individual, because everything is dead.
Yes.
So,
So we are.
so the model, yes. So the point is that in these models here, this one-dimensional model, like logistic growth, we are hiding something under the carpet, right? And what we are hiding is that we are modeling the population, but we are not explicitly modeling the resources, right? So we are saying the population is a dynamic variable, right? It changes over time because there are resources, they reproduce, they die, etc. So we model the n. But then there is something else, which are the resources, right? And if we start from one individual with many resources, also the resources are going to change, right?
Yeah.
We are not modeling that. We are sort of putting it under the carpet. But we are putting it under the carpet in a smart way. And the logistic growth is basically the result of this putting the resources under the carpet. What is the smart way? The smart way, and we're going to see explicitly that, is you can imagine to have a model where you consider resources and population together. But then you say, let's say that the resources change on a time scale which is much faster than the individuals. Okay? So basically you add one individual, the resources are going to respond immediately and go to the stationary value that corresponds to that population. Right? If that happens, you can basically sort of integrate out the dynamics of the resources because it follows immediately the one of the population. Okay? And therefore you end up with one equation which has all the characteristics of that. Okay? We're going to see of the logistic growth.
But for example, let's take the example of certain birds that live in, let's say, the Amazon rainforest and
Yes.
cutting trees.
Yes.
Now, for those trees to grow back, it'll take a very long time.
Yes, the point, yes, that's the point. But suppose that I'm thinking of whales and krill, right? And the things that the whales eat,
Okay.
okay?
Yeah.
For a whale to reproduce, it takes 30 years, right? For krill to reproduce, it takes days, right? If I look at the population dynamics of whales,
Yeah.
right? Basically, the amount of krills you have, it's always equal to to how much they reproduce and how much they are eaten by whales, right? It's always in equilibrium.
Yeah.
I mean, forgetting things aside, of course, they're complicated, but if we think of krill and whales, right? It's not that the population of, you have to take into account the fluctuation of the krill on the population of whales, right? It's only that if you add one whale, you have less food for everybody, but the effect is immediate, right? It doesn't take a long time to respond,
Okay.
right? So the population of krill is what it is given the number of whales, right? Okay? Because they are on two very different time scales,
Yeah.
right? One is years, the other one is days,
Okay.
right? So if we want to look at the population of whales, we have just to take into account their population and effectively the effect of krill. Now this sounds like a little bit like that, and the reason is because I'm not showing you how to do that, but we're going to see that. So we're going to derive logistic growth, showing how it emerges, and other equations which have a similar behavior to logistic growth. So in practice, to answer your question, what is carrying capacity? Carrying capacity is can be due to different processes, okay? But can be, for instance, can be a ratio between fluxes, for instance. How much resources are put in the system versus how much resources are consumed, okay? So if you put resources in the system and you very fast consume them, your carrying capacity is going to be lower. If you put few resources, the flux of resources is small, the carrying capacity is going to be small. If you increase the flux of resources in, the carrying capacity is going to be larger, right? So one way to see it is a ratio of fluxes, for instance, which apply for some system. For other systems, actually, it's much simpler than all the discussion I had. If you have planes, the carrying capacity is typically given by space, right?
Yeah.
Planes, basically, they need the sun. To need sun, you have to be exposed to sun, so you're competing for space in 2D, right? That is the carrying capacity, how much space there is for everybody. Okay? These are two examples of how carrying capacity emerge. Okay? But again, all these parameters, and this is always true, but in particular in ecology, they are always effective in the sense that they are always properties that capture some statistical feature of the population we have into account, right? So the carrying capacity is like, let's say, something related to how much space you have. It's not a property of the individual per se. Okay.
So for example,
Yes.
we model a system. The carrying capacity can describe that the population of that system already, or do we find the value of the carrying capacity given a model?
Okay. So yes, that's a good question. So in a way, it's always a parameter of some specific model, right? But in general, with carrying capacity, what you mean is that you have in mind a scenario like the one in logistic growth, okay? I don't know if I'm answering your question, perhaps not. If I don't, tell me. But what I'm saying is, you always have in mind something like this. So you have this term here, which is the per capita growth rate. In exponential growth, this is constant, and you assume that it decreases over time, okay? And this per capita growth rate is 0 as some value. The carrying capacity is the value where this is 0, okay? This is what you have in mind. Now, this can be a line, like in logistic growth, can be something with a different shape, something like this, could be something like that, etc. Can be the function you want, right? But what the idea is, the carrying capacity is the value at which, on an individual basis, the rate of having birth and the rate of dying equals, right? So exactly when the population growth is 0, okay? And the idea is that this carrying capacity corresponds to some effect that has to do with the limitation of resources, but however broadly are defined. So the carrying capacity is that value there, right? I don't know if that answered your question. Or your question was, how do I measure it?
Yeah, I understand.
Okay. But it's not something that is, in a way, it's not something that applies only to logistic growth, right? Applies to a vast large of models which have this dependence on per capita growth with them. And the idea is that any realistic model must have this dependence, because you don't have infinite resources, or you don't have resources that are replenishing at infinite rate. Okay.
I finished.
No, I hope, no, if it's not clear, ask me again and again and again.
I have a question.
Yes.
In the lecture of local stability analysis.
Yes.
So I remember when I studied numerical analysis,
Yes.
We had the method to discover if a point is stable or no, when we used the simple condition, which is the absolute value of the first derivative of function in a point must be less than 1.
Yes.
What is the difference between, because we found a different result in the lecture?
Yes. So the difference is that you are thinking about discrete models. Okay, I mean, I didn't plan to open this parenthesis, but I think it's a good point of discussion, so let's open it. So the equations we are thinking of are equation of the type dx dt equal f of x. And what I showed you is that, okay, definition of fixed point is this, and a fixed point is stable if f of x star is lower than 0. Okay? The equations you have in mind are equations of the type, of the discrete type, where you have x t plus 1 equal to xt plus f of xt. Okay? So where you have a time which is discrete, and then you basically evolve step by step. Okay? Let's call this g because it's let's call this g for a second. Okay? Now, what is a fixed point in this context? Well, a fixed point is a point where x of t plus 1 is equal to x of t, and so a point where g of x star is equal to 0. Okay? Right? What is when a point is stable? So what do we have to do? What we have to do is, okay, we can compare, let me think what is the best way. Let's say that that xt is equal to x star plus d of x. Okay. So what I get here? I get that x t plus 1 is equal to x star plus d of x plus g of x star of x. Okay? And this is equal to x star plus d of x. Oh, sorry, let me write it this way. Star plus. Okay. Now, let's expand this function here. So this function here I can expand, and I get g of x star plus delta xt g of x g prime x star. Okay? Good. Now, this left hand side I can also define it as x star plus delta x t plus 1. Okay? And so if you put together this term, okay, what I get? I get that this term here cancels with this. Okay? And I end up with delta x t plus 1 is equal to delta x of t, right? 1 plus g prime of x star of, yes. Okay? Correct? Can you see it?
Yes, yes.
Right? This is what you get. Right? Now, when are you stable? So here you started, let's say, let's look at graphically. Here you are at x star, right? At point t, and you started here, let's say. Okay? Which is x plus, this step here is delta x of t. Okay? Now, at the next step, either you're going to go farther apart from this point or closer to the fixed point. Okay? So you want to know whether you are closer to the fixed point. When are you closer to the fixed point? Well, you are closer to the fixed point where, so you are, let's say, stable if delta x of t plus 1 divided by delta x of t So this ratio between this point, right, is lower than 1. Okay? Okay?
Yes.
Now, of course, you can have that both of them are negative and therefore you have an absolute value. Right? And why do I get, and then I get, yes, and then I get 1 plus g prime of xt lower than 1. Why doesn't it work? What did I do wrong? What did I do wrong? No, it's not there because it's. I'm doing something wrong. Oh no, that's why, sorry. When you write, sorry, I was writing the next step immediately. When you write the equation you have in mind are equations like these. Apologies, sorry.
Yes, yes, yeah.
Okay, thank you, okay. You have in mind equations like these. Sorry. What he has in mind is, you have, sorry.
I'm sorry, I lost.
No, it's because so we consider these, we are gonna consider these. You can, I mean, this is like something that is a deviation from our
This is
trajectory.
chapter number.
This is
This is the next chapter.
this is chapter number. We are not gonna do that.
We're not
okay.
going to do. Oh.
Okay.
Because I was.
But we are doing that.
Yes.
So, but it's because of his question, which is relevant. So he's saying, let's consider a question like this. Okay. Now, what is a fixed point? A fixed point is actually. That's why I was confused by. So he said, let's consider equations like this, which are equations that are discrete, and you say, I'm in point t, I want to know where I'm in point t plus 1. Okay? Right? So he's saying, oh, I have this equation here, what is a fixed point? Well, a fixed point is a point where g of x star is equal to x star, right? So when you are in point x star, then you upload these, and then you are in point x star. Okay? Now let's expand around the fixed point. Let's expand around the fixed point. This is correct. This is correct. This is not there. This is not there. Okay? You have that. That is 0. And therefore you are like with this equation here. Okay? There is not just the 1. Right? That is just the equation. I just plug this expression here inside the g of x. Obtain this. Obtain this is just equal, and then I have this expansion. And then I have this equation here, where they are just multiplied. And then I want to say, is this fixed point stable or not? well, I want this ratio to shrink, right? I want that the deviation from the fixed point becomes smaller. So if this ratio here is smaller than 1, and this is true if g prime of x star is lower than 1. Okay? Now, what is the connection with what we have done? Well, let's say that I mean, where do you think is going to be the connection with what we've done? I'm talking to you.
Yes. Can you repeat?
Now the question is, where do you think is going to be the connection with what we have done, right?
No, it was a question because I had the visual intuition for derivative,
Yes.
but it is how the function diverged from its values. So if we found a derivative in a point bigger than 1, then the value of function, they are going further than the function than the
Okay.
x's.
Okay, let me do this so perhaps it's clearer the point. So you have this equation here, right? Can you see it?
Yes, yes.
Yes. You have this equation here. Now let me define a slightly different equation where I say I don't move to time t plus 1, I move to time t plus delta t. So I just say x of t plus delta t is equal to g of x of t, right?
Yes.
Okay? And then let me define another function which I call, I can say that this is equal to x of t plus delta t f of x of t. I can always do that, right? I can always redefine this function in that way. Okay? Right? I can already define that function in that way. And therefore, what do I get? I get x of t plus delta t is equal to x of t plus delta t f of xt. Okay? And here it's obvious that if you send this delta t to 0, then this becomes a differential equation. Okay? Now, okay? And the point is, what is the point? Is actually the fact that you have a discrete equation here matters only if you are doing big jumps, right? If the jumps that you are doing are very small and you just move locally, you can effectively approximate these with a differential equation. Okay? Now, where does the stability criterion enters in, right? So if I look at this derivative here, what do I have to substitute here? Well, g of x is equal to x plus delta t f of x, okay? But therefore I can write what is g prime of x is going to be equal to the derivative of this expression here, which is 1 plus delta t f prime of x, right? Okay? So the condition for stability of this equation here is 1 plus delta t f prime of x lower than 1, right? Okay? Now, important point. Here I have a delta t, okay? So this term here, I mean, I want to consider the case where delta t is small enough. When delta t is small enough, this term here is not going to change the sign of this expression here, right? Because this term is small, so it's never going to be lower than minus 1, lower than minus 1. So I can remove this absolute value, and I get this one lower than 0. And I can forget about the delta t.
Which is the same condition.
Exactly. So the point is that the two things are equivalent, and the connection is due by the fact that when you have a discrete equation, and that discrete equation change very slowly with time, you can effectively approximate that equation with a differential equation, and the stability condition is translate correctly. Okay? Okay, yes. So now let me say something because we introduced it. These discrete equations are interesting. I mean, they are actually extremely interesting. They have very interesting behaviors. They are meaningful to model population dynamics. For instance, if you have plants that reproduce, that are annual plants, so that they reproduce every year, you don't have things that reproduce continuously in time. They have a population now, and then you're going to have a population next year, which is some function of the population you have today. So you have to take into account the discreteness of the time of the reproduction, right? And therefore, they are meaningful. They are interested. They have many interesting properties. We are not gonna spend a lot of time on them now. I'm gonna mention them at the very end of the ecology part where we look at chaos. But for now, we stick to differential equation, etc. But I hope that the connection is clear. The connection, the two equation, not the internet connection. Okay? Yeah. Okay. Good. Okay. Other questions?
Application of the numerical methods.
Yes. The numeric. Okay.
Yeah.
The numerical methods. What is the question?
The question is, could you give us a problem to apply? Because
Yes. Now. I can give you now.
Okay.
I mean, you're gonna have a problem to apply it, but I
No,
can
on
give
the
you.
computer, like when we're actually doing it. How
Yes.
should we be applying that?
So you want to know how to solve the problem I'm gonna give now? Okay. So so for instance, let's say this is a simple exercise you can try. Simple. I mean, it's an exercise you can try to solve, which is sort of basic, and you can play with it. And you can say, I want to integrate this equation here.
DP or DP?
Oh,
Yeah.
thank you. Sorry. Okay. We saw this model, right? You want to integrate numerically this. Okay? So you want to say, if I start from a given initial condition and 0, you want to plot n of t versus time. Okay? This is just one example, right? Where I say 0 is lower than a, which is lower than k. Okay? We already know what is going to happen. We know everything, but it's a good exercise exactly because of that. So we are going to learn, I mean, you can test whether you get what you expect. The question is, you have to integrate it numerically. Now, I'm completely agnostic on the method you use, in the sense that you can use the method you like, the package you like, the software you like, etc., etc. But since you have seen Python, or you are seeing, I don't know, you have, yes. Since Python is a good solution, is modern software, blah, 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 I encourage you to use Python. And in particular, there are functions which is SciPy. I don't know, I think SciPy optimize or something like that. It is in my note in the lectures. So the point is, I don't have. I'm not able to write a code on the board.
Of course.
But if you want, I can give you like the code that integrates this equation.
I want to learn how to integrate.
Yeah, no, okay. So you want to do, okay. I mean, I can give you the solution. I mean, there is going to be an assignment where you have to integrate things.
Yeah.
But if you want to try it, I think you just read the documentation, and it's I mean, to integrate one-dimensional nonlinear equations, it's pretty standard. So you should not have problems to do it. Here you have many options, which includes the methods you use to integrate the dynamics. Everything we're going to use is going to be pretty smooth and doesn't require to use the super fancy, weird named method. I mean, you can use standard Runge-Kutta, Simpson, these kind of things. My point of the class is, this is not a class about numerical methods, right? So I don't want to go into the details of what is the best numerical methods or recipe to solve nonlinear equations, blah, blah, blah. I'm saying there are many methods, there is a whole fields of study. I mean, it's very interesting, you can go into details of that, but the best approach is, let's take something that is already written, that is efficient, and use it, okay? So I'm not sure that is SciPy optimized.ode, but you can check. I can add the link to Slack, for instance. This is something.
Thank you.
Yeah, if I don't do that, remind me on Slack.
Can we use the solvers
The-
for these? Like
There
for
are-
example, Berkeley, Madonna, they use from Capita.
Sorry?
The Berkeley Madonna solver. Can we use that to solve?
I don't know the name. What's the name?
Berkeley Madonna.
I don't know it.
Yeah, because there is no code. It uses the Numerical method.
Okay.
And then you only plug in the differential equations, and then it will give you the solution.
Yeah, I mean,
We use those instead of
well, I mean, the point is, if it is, I'm not sure, but what it is like a software. It's,
yeah, yes.
I mean, you can use it, but the point is, I mean, the point of this is that Python gives you the flexibility to interrogate everything you want about the dynamics. You can look at the trajectory. You can.
Yeah.
I mean, if you can, yes. I mean, in general, in the assignment, I give you when there is going to be something about solving equations. I don't care about the way you solve it. Right? In the same way, I don't care if you use a pen or a pencil to write on your papers. Right? The point is, whatever you use, the goal is that you are able to interpret the result of that, to connect that you are not just blind and you just press a button and you receive. Right? The goal is to interpret what you get. So you are free to use. I will never ask the code. Right? I will never ask to show me the code. Given that, I think that learning how to use Python is way better for your future and for. I mean, it goes beyond solving differential equation, which is something easy somehow, but numerically, I mean. But being familiar with Python, it's very useful for you in general. So know how to plot things, etc., etc. It's good. Okay. Yes.
Can you explain more about why do we characterize between weak or strong alleles?
Okay. Yeah, so now I'm going to write G, and there's a different meaning from this G. So let's say that we consider equation of the type, okay? So what is G of n is this per capita growth rate, right? Is what is the difference between the number of births, the rate at which one individual gives birth, minus the rate at which one individual dies, given a population, okay? So if we have exponential growth, this is flat. If we have logistic growth or similar, this is going to decrease, right? What we're saying is, when you have an allele effect, this is going to increase initially and then decrease, okay? Now the difference is between weak and strong is that in the weak case, G of 0 is larger than 0. Actually, I should, if you want, the limit of n going 0 plus of G of n is larger than 0, okay? So this is weak, and in the strong case, this is negative. In practical terms, what does it mean? That in this case here, there is a critical threshold of the population, A, below which the population go to extinction. Above, it will always grow. So if you look at the trajectory of the population, okay, and you start from any small number, in this case, in the weak case, In the weak case, it's going to grow and go to chemical capacity. Now, the growth here is going to be different from the logistic case. I mean, it's not going to have the same shape, right? Here something is happening, but still, like, the qualitative behavior is the same, or the long-time behavior is the same, okay? In the strong case, you have K, and you have A, okay? So if you are below A, above A, you do like this. If you are below A, you go to extinction. And it's because the growth rate here is negative. Right? So in practical terms, it means that if you are in this strong or obligate early effect, you need a critical mass of individuals to grow. Otherwise, you just go to extinction.
We have the MVP, minimum viable population.
Eh?
Minimum viable population.
Yes, there is a minimum value of the population for which.
I think it's 160 for human beings.
Ah, I didn't know that. Okay, yes. Is 60.
160. 160.
Ah, 160. But there was a, yes. Well, but I guess, I mean, I don't think it's, I mean, the point is what gives rise to that minimal value, right? I mean, it's not clear, right? Because you can have, you can imagine that you have two individuals giving rise to a whole population, even if you have just two, right? I mean, if there is, yeah, if there is 1 million of it, right? So, in principle, I mean, the point is, I think that numbers come from also like some sort of society. I mean, how likely is that two individuals are going to survive by themselves without a society, right? Without a group? So it's, I mean, all these equations have a statistical component in the sense that they describe what do you expect on average, right, in a population. Then you have clear fluctuations when you have small numbers. But yes. Yeah. Yes.
So for example, for this, if there is an alley effect, I see that the weak alley effect is safer, or is it's better for a system?
Well, okay. So this is a very long. I'm gonna sit down for this. No, it's a very good point. I mean, it's not a negative sign that I sit. It's just that that's a very good point. So this is actually so you are saying something about what is better, right? What the word you use. The point is, what do you mean to be better, right? I mean, what is the you are implicitly assuming that there is some function, which let's call it value or utility, and somehow that population is maximizing that value or maximizing that utility, right? This is, I mean, this is okay. I'm not I'm just saying this is what you implicitly are saying when you say better, right? That there is something you can. Now the question is, what is this function? Think about humans, right? What is the value? I mean, what is the function we are trying to maximize? In what sense something is better or worse?
No, I mean better for a population.
Yeah, I know. What does it mean to be better for a population?
If you're talking about like the Malthusian theory, you
Huh?
don't have a population.
Sorry? No, I mean, one thing that you can say, what is better for the, this is the point where I'm going to, but one point that you can say, what is better for the population is to avoid extinction,
Yeah.
right? You can say this is a legitimate.
But not to overcrowd or overpopulate.
No, you can say it's over time. You try to minimize the probability to have extinction at any unit time, okay? So this is my utility function. The problem is that this is not really what populations are optimizing, right?
Yeah.
It's not, I mean, here we are also introducing something implicitly, which is the possibility for population to change all these values, right? When you say, I want to optimize, this is a safer choice, is because you say, oh, there is someone with a large value of A and someone with a low value of A, and comparing the two, right? So you are comparing population with which have some variation, right? Okay. No, it's hard because it's hard to read the face with the mask. So I'm trying to interpret what you're saying, right? So I think this is where you're going. You are the scenario you are imagining, and it's a very good question. So the scenario you are imagining is, I have a population, but actually I have I have a variability within my population. And this variability corresponds to different, for instance here, value of the parameter A, or in general corresponds to some difference. And somehow I want to know what is better, right? Now, in saying that, you assume that there is some implicit notion of better, which is what you think is better, right? Which is, for instance, avoiding extinction, right? Because it's something that arguably will all give value to, right? We don't want the human population to go extinct. The point is that, so when you're thinking of a population with some variation, what you're thinking is to evolution. We're going to discuss that in the second part.
But I have a comment on that.
Yes.
For example, if we're thinking about extinction,
Yes.
and if we think about, let's say, the dinosaurs,
Yeah.
they didn't see it coming. They couldn't stop it.
Yes. But
if let's say an asteroid crashes into Earth and
no, yes,
triggers an ice
but
age,
no,
we can't
that's
do
true.
it.
So there are okay. The point is that yes, there are all these exogenous things
Yeah.
that yes, I mean, you're walking on the street, there is someone coming on your head, you couldn't foresee that, right? So that is on a side, right?
Yeah.
Let's say even like a population that lives like very nicely in a very fixed environment, etc. Right? Everything is controlled. They know everything about the environment. Somehow we have this notion that the best, I mean, what is going to happen is, or the population wants to do, or is going to do what is best for them, right? And best is avoiding extinction, right? The point is that evolution does not work that way, right? So evolution does not work in an optimization sense, okay? Does not work in the sense that you are trying to optimize. We're going to discuss that in the second part of the class, but it doesn't work in the sense that you are trying to make things better and better, okay? Even if sometimes the notion is that. You cannot say it's clearly better for a population to have a larger A, because then you don't have this critical mass, therefore they're going to do that, okay? You cannot say that because evolution doesn't work that way. You can write a very simple model, so very simple model in the sense, a very simple scenario, where you see that the population evolving actually go to extinction. Just because individuals, the individuals that are more likely to reproduce are individuals that are more greedy, that use the resource less efficiently, and therefore the population size decreases over time and it goes to extinction, right? So there is no, it's important to, especially when we're thinking about ecology and evolution, or at the boundary between the two, of not putting in what you think it's going to be better in the long term limit, right? So there is not a priori utility function you are trying to maximize. That's why this is a very good question, because it's right on the point of something that is very, let's say, something that I really want you to understand or take away from this class. Yeah.
With ecology, the time scales can both be less and, large and small.
Yes.
But in evolution, the time scale is always huge.
Depends.
Well,
If you have bacteria,
yeah, it does.
If you have bacteria, I'll show you.
No, that's true. Look at COVID; it's mutating so quickly.
Yeah, well, that's okay. That's another point. Yes, there are 2 points. There is the time scale of mutations, which are basically the time scale of reproduction. And then there is the time scale of evolution. You want spoilers from the second part, and it's like very hard to abstain from giving you spoilers. But yes, so the point is, the time scale of evolution is not necessarily small. In the sense that you can have change that accumulates in a few generations. And you can really see, for instance, evolution in bacteria where you give, I'll show you, no spoilers.
Okay.
Yes. Yes.
So according to the equation which you write, what's the meaning of A?
Yes, so A is the minimal size of the population to have a positive growth rate.
And according to the second graph, I
Yes?
can say A can be negative. Or we are talking about the population. The population can be negative.
No, because there is the n in front, right? So there is this n in front here. So if you start, this is 1 over n, the n dt, right? This is the per capita growth rate. So there is, I'm dividing for this n, okay? So I'm looking at, if you have an individual, at what rate it reproduces, minus rate it gives births. If you look at dn dt, so how the population grows, not the individual, you have to multiply this by n, okay? And what you get is that when you are very close to 0, you multiply this for a number which is very close to 0. So you get that the population growth rate is something like this, okay? Because if you are, the point is, if you are in 0, if there are no individuals, there is no one to reproduce or to die.
But in this case, what's the meaning of the minimal point?
This point here,
Yes.
this is the per capita growth rate, which is in this case is negative, so they tend to die more than they want to give birth, as the population tends to 0.
Is it greater than 0 or less than 0?
It's less than 0. So it means that if you have an individual, it's more likely that it's going to die than that it's going to give birth.
But the problem is that you can have the population less than 0.
No, here you cannot.
But why the graph shows us that we can have the population less than 0?
No, the population is, so this is a plot of the growth rate
Yeah.
as a function of n. So here, here you cannot access, right? But clear, my point is that if you start from any positive initial condition and you follow the dynamics, you'll never end up with a negative population.
Pardon?
Eh?
Can you repeat?
If you start from any positive initial condition
Yes.
and you integrate the dynamics, you'll never end up with a negative population. I can, so let's consider explicitly that equation, right? With this choice here. Okay? Let's look at the n dt when n is very, very small. Okay? When n is very small, I have Rn, then I have the second term, right? N is much smaller than k, so I can neglect that part. So here I get 1. And then n is much smaller than a. Okay? So I can neglect this. So I get minus a r n. Right? So there is this n. Right? So this is like exponentially decreasing with n, with the rate AR. So it means that if I start with any, here I'm always like with n 0 much smaller than a, much smaller than k. This is going to decrease exponentially. The population, sorry. Okay. Now, this is like what happens in this equation. So you never cross 0. There is an important point here that we are always considering n as a continuous variable, while clearly you cannot have 3.6 elephants, right? So there is an approximation here, which is we are considering large numbers, right? So clearly when you're close to 0, the approximation of considering large numbers breaks up, right? So what is going to be relevant there? What is going to be relevant there is stochasticity and randomness, right? Which also emerged in a previous question. So that part is going to be covered at the end of the ecology, beginning of the evolution part. So that is exactly the transition you have to make to look at evolution. But putting this aside, okay, in this equation here, if you start from a positive initial condition, you can never cross 0. And the reason is that you have this n in front, right? So as soon as you hit 0, this is 0, right? Because you have always this n in front.
You said something that I wonder about. You said if we start with the positive condition, since you are talking about population, you can't start with negative condition.
You can never, exactly. You cannot start from negative.
That means we don't need to talk about positive condition.
Mm-hmm. I didn't understand.
Since you said we can start with a negative condition, and since we are talking about population, we don't.
Yes.
It's not. We can't say a negative condition. You can just say the initial condition, right?
Yes. So the point is, in all these equations, you can never change sign, right? Let's, for a second, pretend that these are not populations, that this is something, right? According to this equation. Now, the point is, you can never change sign. And the reason is because you have this n in front, okay? Now, since we are considering populations, then all the initial conditions we have are positive populations, so you always stay positive, right? As intuitively should be.
I think he means what types of conditions are we talking about?
What? Sorry?
What type of condition are we talking about?
No, I'm not talking about the type of condition.
Then
Understand? Yes, I understand well. But actually, if we plot 1 over n, we have dn over dt, and according to the unit of the other side, it's still the unit is still, if I consider the population, the unit is still the population.
Mm-hmm.
That means the negative part, I still have the problem about that.
Well, but you have to consider this as, I agree, but this is like a per capita term.
The,
per capita.
So a per capita, per individual. So this is what, so this term here is, this is, what is this? How should you interpret this? This is the rate, so it's the probability per unit time, right, of birth minus death. So this is the probability per, this is very important. This is the probability per unit time. So it means that, and it's a rate, right? I said the word probability while everything here is deterministic. But the point is, what you're thinking is you have, let's say that you have one individual, right? There are only two events that can happen. Birth or death, okay? What I'm saying is the difference between these two rates is equal to this, okay? But it's, even if you have one individual, either of the two is gonna happen, right? And this is what happens on average, if you want, okay? Here I'm looking at the average behavior. So you can interpret it that way. If you have this equation here, and you have one individual, on average what is gonna happen? Well, some are gonna give birth, some are gonna die. On average, it's equal to this, okay? Right? But that doesn't mean that you have one individual, then the only thing that can happen is give birth or die. If dies, then you have 0 individuals, you are in 0 and nothing happens, right? Okay? The point is that whether you consider discrete individuals, as in reality, or you make the approximation and you consider continuous individuals, right? In both the cases, you can never cross 0. Okay? Yeah. I'm not sure if that answers your question or. So I understood that your issue was with this plot here, because you were saying, when here you are at n very small, and here you have something that is negative,
yeah.
and can be arbitrarily negative. And being arbitrarily negative, you could cross 0. I understood that this was your issue. But the point is, I mean, these are always like rates, so what happens in the next unit time is still a small effect if you want, right?
What?
Huh? So it's still a small effect, right? So even if you have, let's say it like this. Even if you have one individual, right? When you're looking at what is the NDT, right? So what we are plotting there, okay? Or let me write it this way. Actually. Let me do it this way. This is the equation we wrote, right? Because I just expanded it, okay? And then you say, well, suppose that n is very small. You are here, okay? And you say, well, you could jump of a large number, right? And you could cross 0, okay? Now the point is, how do you cross 0? You cross 0 if 1 plus g of n delta t is becomes negative, right? I discretize the equation and I ask, when do I become negative? Right? You agree? Now, to become negative, that means that g of n times dt is lower than 1. Right? So you see that the problem, here you negative. Now, the issue here is that I'm considering differential equation, so I'm considering the limit of delta t going to 0. So no matter how negative is g of n in 0, okay, no matter how this is small, delta t, I should always choose delta t such that this is small. So this is it's negative if, if plus lower than 0, so this is lower than minus 1. So no matter how small this, how negative this is, I should always choose delta t such that this is a small number. So this will never be lower than minus 1. Because we are always considering differential equations, right? So you cannot have big jumps. You see what I mean? Or so you can never cross 0 here. Because, I mean, the equations you are integrating, so dn dt over n does like this if you want. Because you have the n that multiplies and is therefore very close to 0, this becomes 0.
We forget about population in this case, right?
Yeah, what I'm saying is that if you have an equation like this, you never cross you never change sign of n. That's my point.
Okay.
So if you start in the positive, for positive values, whatever are the values of k and ka and the parameters, you never cross because you have this n in front of everything. And therefore, as soon as you are 0, this becomes 0 and you are in a fixed point and you don't move. Okay, yeah.
But,
Go ahead. No, go ahead.
If there is no effect,
Yes.
if n is 0, it can still, it's not extinct.
Well, here, yes. If n is 0, here you have minus a. Here you have 1, but there is this n here. So all this term here is 0. So n, I mean, in these models here, it's 0 is always a fixed point. Right? You can say, oh, I have migration. Okay, great. You have migrations. There is some rate where individuals come. But still you cannot cross and become negative, right?
Yeah.
Yes, because this very close to 0, this is going to be 0, and this is going to be positive. So this is going to be positive. Yeah.
Please, can you explain again the process to find the stability point for pitchfork bifurcation.
Okay. So I'm not sure what exactly what in particular you mean, but I can sort of summarize. Let's do this. I'll summarize the whole thing about pitchfork bifurcation, and you stop me when I say something that you don't understand. Okay?
Okay. About the pitchfork.
Yes. So the pitchfork bifurcation is emerging system. Now, let's consider a system which is not a population. So the value of x can be arbitrary. Okay? And we consider the case where this f of x has some symmetry. Okay? Has this symmetry here. Okay? What this means is that the trajectory of the systems are like in a mirror, right? So if you start from positive values and it's going to become smaller, you start from the negative values, it's going to become larger like in a mirror. That's what it means. And this is equivalent to say that v of x is equal to v of minus x. Okay? Right? And basically, what do I say? Well, you can, let's assume that you have a bifurcation point. So, if you have this, sorry, let me say something. If you have this condition, right, clearly a consequence of this is that f of 0 is equal to minus f of 0, right? Which then has to be equal to 0, right? Because you have a value equal to minus its value, therefore it's 0. So that means that x star equals 0 is always a fixed point for any value of the parameter, right? So we'll always have the fixed point x star equal to 0. So what we can do is that we can expand close to the fixed point and close to the bifurcation point. So let's assume that there is a bifurcation point in some QC, okay? And then we define the Q equal to Q minus QC. So I expand around this point here, okay? And around the fixed point. So I want to write dx star is equal to, and I start writing the terms, right? I start writing the terms, and one thing that I realize is that exactly for this condition here, I have that all the even derivative in 0 have to be equal to 0. Okay?
Is it 2k?
Yes, 2k. Where k is 1, 2, etc. Okay? Yeah, okay. Right? So when I do this expansion, okay, what I get is that there are only some terms that that are there, right? So all the ones where I have the odd derivative disappears, etc., etc. And what do I end up with in the normal form? I end up with delta q delta x minus delta x cubed, right? Do you remember correctly? You can correct me. It was like this. Plus or minus, yes. Okay. Why? Because I have the term. Yes, because when I take the derivative over delta. So let's write all the terms. So I have okay, f. So here I'm considering that I have the dependency on x and the dependency on q, right? And I'm expanding around x0 and q equal to qc. So here I would have, in principle, okay, f of 0 qc which is 0 because that's a fixed point. Then I will have df over dx in 0 delta q, delta x, sorry, right? Then I have delta f dq in qc, sorry, in 0 qc, 0 qc, delta q plus all the second derivative, right? df q squared 0 qc plus t squared, etc. all the terms. And what do I have? Well, this becomes 0 because I'm just deriving this term by dq, both of them, so this is 0, right? Then this one is 0 for the same reason, this one is 0 for the same reason. Here I have the mixed one, which is not 0. And then I have all the higher terms, okay? And why this one is 0? Wait. Yes, so the terms that I have is like delta x dot equal to, let's say, some parameter a delta x plus b delta x delta q plus delta x cube minus c. Okay? These are the only terms that are not, the first terms that are not 0. Okay? Now, here I can write it as b a delta x 1 plus b over a delta q plus or minus delta x cube times c. And then I can redefine the parameter, I can redefine all these one as control parameter. I call this r, and this one is x plus or minus. So I end up with an equation which is x dot equal to rx plus or minus x. Okay? And the point is, when I do this game of the normal form, I can always redefine the time scale or the parameter. Because I just want to know what is the behavior of the equation. I don't care about in what unit of measure I'm measuring x, in what unit of measure I'm measuring q, in what unit of measure I'm measuring t. So you end up with that normal form. Okay? And your question is stability of that.
Yes.
Okay. Took a long way to answer your question, sorry. I should have started like this. You want the one with the plus or the minus?
Minus.
Okay. So fixed points. You can write this as x r minus x squared. So fixed points are x equal to plus minus square root of r, assuming that r is positive, and x equal to 0 always. Okay? Okay. Stability, which point you want to know the stability of? 0?
Yes.
So let's take the derivative of this. So let's call this f of x. Let's call it g of x. So the system is stable if dg over dx in x star is lower than 0. Okay? So what is dg of dx is r minus 3x squared. Right?
Yeah.
Yes. So, is 0 stable? 0 stable? Well, I substituted here 0 and I get is stable. So, stable if r is lower than 0. Right? And is plus or minus square root of r stable? Well, it's stable if 3r R is lower than 0. So if minus 2R is lower than 0, so if R is larger than 0. So X star equal to plus or minus R, stable if R is larger than 0. Okay? So what I get is that I have the fixed point X equal to 0, which is stable if R X equal to 0 is stable if R is negative, and then is unstable if it's positive. And then I have plus or minus square root of R, which is stable. Okay?
Is R considered a parameter?
Yes. But you have always to think of, you start from a complicated equation, I mean, whatever it's Q, whatever however it is defined, and then you look in a local neighborhood of the bifurcation point. So you just zoom in as the parameter change close to the bifurcation point and as X change close to the bifurcation point. And you are describing the system close to that point. So you should think at this of a magnification of, like, zooming in what's happening close to the bifurcation point and close to X, to the bifurcation point for R and for X. Okay? So it's really zooming in this point here. Okay? Then, of course, what happens to the system can be different on larger points. But so the shape of this is not plus or minus R, right? It's plus or minus square root of R if you are far away. But close to the fixed point, whenever you have a pitch for bifurcation, it's going to be like that. Right? So an example is, suppose that you take, let me think, suppose that you take something like X dot equal to R sine of X minus sine of X cube to the fifth power. No, sine of X cube, let's do, actually, let's do like this, okay? This one is something that is going to have the same behavior close to the bifurcation point, right? The reason I know that is because, like, this is a function which has the right symmetry, and if I expand X close to 0, right, I get X and I get X cubed, right?
Can I?
Yes.
So for example, if we are characterizing a system, we find the bifurcation points and unstable or the unstable and stable points. So why do we need to, or do we need to name, like, if we get the bifurcation point, I will say that it is a saddle line.
Well, I mean, okay, that's a fair question. So why do I need to know all this taxonomy? I mean, it's not particularly important, actually. I mean, it's not something that's going to be central in the class to classify bifurcation points. The reason it's useful to know is, okay, it's because it's a huge field in mathematics, and it's much more complicated when you have systems which are not one-dimensional. Okay, so it's interesting by itself, but it's useful to have an idea of what kind of things can happen, right, as you change parameters, right? So, for instance, it's good to know that the difference between transcritical and fold bifurcation. And the reason why it's good to know is because if you have something that has a transcritical bifurcation, you expect it to change slowly and, in the ecological example, go to extinction. If you have a fold bifurcation, you know that some sort of sudden big change can happen. So a collapse of a population can happen. Okay, so that's why it's useful to know these names, but it's not something that is central. Right? We'll see other type of bifurcation in 2 dimensions, and there are limit cycles, okay, whatever. But it's just to have an idea that these things can exist, right? And there is a sort of finite types of way the system can change fixed point behavior with parameters. And also because like this is the first, I think the fault bifurcation, the example we saw about fishery, is the first case we saw in this class of something that you could not have guessed a priori. Right? So the point is that we have a very linear way of thinking, right? And so we think that, oh, if I push this, that is going to react in that way, right? While when you have non-linear systems, it's much more complicated because you have these weird feedbacks. And therefore, the fault bifurcation was an example of something that you just push it off a little bit and it explode, right? We're going to see others, but I think it's a good angle to have an idea that, to give you the idea that nonlinear dynamics is not just, I mean, it's cool because you put into some ingredients and then you get some unexpected behavior which is not obvious a priori. Okay? Yes. So, but again, the bifurcation points, it's important that you know that they exist, that these are sort of part of a discrete classification, but we are not gonna dive into this classification and know all the little differences when we gonna go to higher dimensional systems. Okay? Good. Other pressing questions? Yes?
I noticed that when you have a loop in a curve, you can define if the point in the curve is stable or unstable. How do you know that?
What do you mean on a curve?
I want to say, I noticed when you have a loop on the curve, you can say if.
Oh, I see what you mean. The graphical methods, you mean?
Excuse me.
Yeah.
Can I leave this session?
Yeah, yeah. So if you look at, so the point is that if you look at x point x, okay, and you look at the sign of this function, let's say that is something like this, when this function is positive, the value of x dot is positive, so the value of x is going to grow. So I put arrows like this, right, for instance. And when it's negative, it's going to decrease. And when it's positive, it's going to increase. Okay? So if you are, the points where this is 0 are by definition the fixed point. So if you have a situation like this where the arrow points away from the fixed point, this is an unstable fixed point. If they point toward it, this is a stable fixed point. Okay? So all these things, I mean, this one, the potential, the Lyapunov function, etc., are all things that work very well in one dimension. As we move to higher dimensional system, we're going to see that it's much harder to use them. But it's important that you, I mean, it's very useful for a one-dimensional system because you have just to plot the function.
How realistic are one-dimensional functions?
Nothing is realistic, but it's a good approximation of reality sometimes, right? The point is sometimes it's a good approximation. You can neglect all these complications and effectively model your population as a one-dimensional system, right? But per se, one-dimensional systems are, I mean, if you have a
For example, in a lake.
sorry?
For example, in a lake, you can just,
Yeah, I mean, yeah, the point is that it's never true one-dimensional because always you have resource. I mean, let's say if you have like plants and you have the sun and everything is constant and they have that amount of space, that is well defined. I mean, that is very well approximated by the one dimension in the sense that you can neglect the interactions
But I
with
think that would only work for cactus because they need very little water.
Well, I mean, the point is, again, there is no, I mean, any model is an approximation of reality, right? So there is no universal recipe on when a 1D model is a good approximation, but I mean, in some sense, you try and you see if it works, right? But the point here is not to, I mean, we never write in this class a model that describes all the phenomena in life, right?
Yeah.
The point of writing these models is to capture some aspect of this complicated reality, right? And hopefully it captures this aspect in a sort of consistent and self-consistent way. Okay? Yes. Good. Other questions? Yes.
So, for example, if we already have a function or an equation for a model of a system, for example, if I see that it has symmetry, is it like, oh, I should expect that it has a pitchfork bifurcation?
Well, you know, I mean, yes. So if has symmetry, you know that pitchfork bifurcation can occur, right? So if you don't have that symmetry, you already know that there is not a pitchfork bifurcation. But you need to have that symmetry. The fact that you have a symmetry doesn't imply that you have a pitchfork bifurcation, right? Because it depends on what value of parameter you can access to, right? Because that is the other point, right? That here we are saying, oh, you have this R and you can change your R from minus infinity and plus infinity. In practice, that's going to be something, right? And perhaps that something is something that can take only positive values. So it's not, you're not guaranteed. The point is to know what can happen in one-dimensional system, right? And to know that there are things that are unexpected a priori.
So for example, for these three bifurcation types, like it is good to know so that when, for example, someone is presenting their work and like they said the word transcritical, so I already know what's happening in their system.
Sorry, I missed the first part. Yeah.
And it's good to know about this type of bifurcation only so that I can understand other people's work.
No, I'm not saying that. No, I'm not saying that. No, sorry. No, what I'm saying is it's useful because whatever model you are working on, you know that there exists a sort of few prototypical way you can lose stability of a fixed point, right? So you don't have 3 billion types of bifurcation. In one dimension you have 3, right? So you know that if you have a bifurcation point is one of these 3, okay? Now that doesn't translate immediately in what do I do with that, right? It's like, oh, derivatives, what do I do with that? Well, I mean, you use them, right? So it depends on what is the specific applications you have in mind. The point the reason why this is interesting is because, again, there is a non-trivial dependence on parameters, even if the dynamical behavior is trivial. You have only fixed points. Right? But you should think of this as a tool in your toolbox, right? So you know that these things exist.
And how
Yeah.
that's good. You always use U equals N over G, and K is the carrying capacity. So it is the units are population. So is U something?
Well, yeah. I mean, I'm just measuring population in units of carrying capacity. So I'm saying the carrying capacity is somehow the maximal population size you can substitute. I mean, it's defined as we said, so you are measuring it in those units. Right?
Yeah.
Yes. Good. Other questions? Great. I have 10 minutes and then I have Zoom session on Skype. So Zoom session on Skype, I said yes. Okay, no. So very good. So thanks a lot for all the questions. Was very good for me. So I'll upload the other videos and we'll meet again next week. Again, so if you have like some pressing question clarification, post it on Slack. Otherwise, we can discuss these next time. Okay. I very much enjoyed the discussion. I really miss being in front of people and not in front of camera. So thanks a lot for the discussion, guys. So let me stop this.